On the Seams tab, the seam arrangement is shown against an image of the mesh. For this example, we'll choose to divide our mesh into two panels. The green lines indicate the positions of the seams. Since we have two panels, we have one seam going down the center. The points where the seam lines cross the mesh edges define the beginning and end points of that seam. Between the beginning and end points, the seam is curved to follow the overall shape of the mesh. This produces seams that are evenly spaced in the mesh and visually echo the shape of the sail. These are usually the best looking seams, but they can result in excessively curved panel edges. To make the panel edges straighter, we can specify straighten seams. This will attempt to straighten each seam and will minimize the panel edge curvature. Note that it is not always possible to straighten the seams, and generally, straight seams do not look as appealing as the natural seams. The cyan lines, here, here, and here, show the warp direction for the paneling and are spaced apart by the roll width. This allows us to judge whether our panels will fit on the roll. The cyan lines can be moved sideways to help with judging if a panel will fit on the roll by holding down the right mouse button. If we are happy with the default seam positions, we can go ahead and calculate the panels at once. Click the Calculate Panels button. Normally, the paneling progress is shown in green. If there are warnings, they will be in orange, and problems that prevent paneling will be in red. When we tell the program to calculate the panels, several things happen. First, the model is flattened to create a 2D fabric panel. During the flattening process, the panel will have to distort some. Shade sail can usually take up to 10% distortion without showing any distress. The amount of distortion, also called shear strain, is reported, and if it exceeds the 10% limit, a warning is given. Here our shear strain is at 2.5%. Also note that the program shrinks the panel slightly to allow for stretch on installation. This is the stretch compensation shown here. The amount of shrink is specified on the materials page. It's defined in terms of warp and weft, and applied in the warp direction defined by the cyan lines. Next, hem and seam allowances are added to each edge, and the panel is dimensioned so that it can be laid out on a lofting floor using triangulation. The curved edges are then defined by midpoint dip values, so that the curve can be approximated by using a bendable rod. Let's go to the Fabric Pattern tab and look at our finished panels. Remember that our units are in feet, inches, and fractions. In cyan, we have the diagonals. Each edge is defined by the length, in green, and the dip, in blue. The white lines represent an edge hem allowance and an internal seam allowance. Let's now go back to the Seaming tab and explore some alternative ways of paneling. For example, we may want to change the position of the seam in order to use the fabric more efficiently. To do this, we would want the mesh much closer to the edge of the roll width, and we would then need to adjust the seam accordingly. The seam lines can be moved by holding down the left mouse button in the green circles. They will need to stay on the same mesh edge, however. Note that the panels will get bigger during the paneling process due to the flattening and the added seam allowance, so you want to be sure that the mesh is well inside the roll width. This time, when we calculate the panels, we'll get the following result. We have one larger panel and one smaller panel, and the fabric has been used much more efficiently. If we try to panel a sail that is not symmetrical, the roll width markers will be angled to match the average center line of the sail. To demonstrate this, I'll go back to the measurements page and load a different example, this time with a triangular mesh. Let's calculate this model, and then we go to the seam section, and we can see how the roll width markers aren't necessarily vertical on the seam arrangements, but are instead aligned with the center of the mesh. When we calculate these panels, we get the following results.